Okay, so last time we talked a little bit about the basics of electricity and a little bit about the basic stamp also. So we're going to go into a little bit more detail about the basic stamp today. We're going to do a little bit more programming about that, but first we're going to do a quick review. So we're going to talk a little bit about electricity. We're going to review some of the key terms that we talked about last time. Voltage, current, and resistance. We'll talk about the units for those, and then we'll do a quick review of programming also. Last time we used the basic stamps to make Morse code. So we'll talk a little bit about how we did that, some of the commands that we used. And then for the lab today, we're going to build on that. We're going to do a little bit more programming. We're going to actually work with motors today. And we're going to make the motors go back and forth, almost like windshield wipers. Kind of appropriate since it's raining cats and dogs outside. So that will be the lab for today. Okay? Also, we're going to talk a little bit about how motors work and sort of the fundamentals of motors, some different kinds of motors, and in particular about servo motors, which is the type of motors that we're using. So we'll talk about motors in lecture, and then we'll actually use the motors in the lab. So you guys have any questions before we get going? Yeah?
I had questions, not extremely related, but I don't know if you've been supposed to have been doing like assignments or group discussion on the Canvas.
No.
I wasn't sure just because you didn't say anything.
Right, no, we don't have any assignments or group discussions right now. We're not going to do group discussions on Canvas this semester. You guys are here together, you can discuss among yourselves. But there will be assignments on Canvas a little bit later on, and I'll talk about those as they come up. But thank you for asking. Thanks for checking. Yeah. Other questions? Yeah.
I was wondering if we needed the Grok's electronic book in class, or if I could just get like a online.
Online is fine.
Okay.
Yeah, we're not going to use it in class. We'll use the lab book in class like you guys have been doing. The Grove's textbook will be used for reading at home, so you won't need to bring that with you to class. And you can use an electronic version. Yeah.
You can get it for free online.
Okay.
Library Genesis.
Library Genesis?
Yeah. Yeah.
Okay. I'm not familiar with that website, but
It's good for us.
so yes.
You said like reading data, like when we start by ourselves, or you will tell us like what to read?
I will tell you, and I'm creating a reading list. This is a new textbook starting this semester, so I'm creating the reading list for that. The first 4 classes will be devoted to the basic stamp. So this is the 3rd class. We'll do basic stamp today and then one more class. And then after that, we'll start going on to other topics in electronics. And that's when we will start with the reading for the textbook. Yeah. Other questions? All right. So let's start with a little bit of a review. Now, we talked about some fundamental terms that we're going to be using throughout the semester. We talked about voltage, current, and resistance. These are all different terms for different things related to electricity. So remember, we saw that cartoon where there were those 3 guys, right? So you can think of the guy in the middle. He was the electricity that was moving along, right? So he was getting pushed by somebody else, And then there was another guy up here who was actually holding on and making it difficult for the electricity to move. So what did we call the electricity that was actually flowing?
Current.
Current, yeah, exactly. So current was the amount of electricity that is flowing through a circuit or through part of a circuit.
On the
Okay?
drawing, though, it's the same thing as average, right?
So
Yeah.
yeah, current is another name for amperage. They both mean the same thing. Yeah. And we'll talk about units in just a second. So what about this guy over here that was pushing the current along? Voltage, exactly. Voltage was the force that was causing the electricity to move. And then this guy up here that was making it difficult for everything to happen?
Resistance.
Resistance, exactly.
That guy.
Yeah, that guy. So that's really sort of a layman's point of view. We can talk more in scientific terms. We said, remember, that all of matter is made up of atoms. And atoms have these electrons that are orbiting around the nucleus. And it's the electrons that can move from one atom to the next. And it's really the movement of electrons is what we call electricity. So electricity is the movement of electrons. So the current here is really the electrons moving along a wire. The voltage is the thing that's pushing the electrons along, and then the resistance is the thing that's making it hard for the electrons to move from one place to another. Okay? Any questions about that so far? All right. Now, we talked last time about how important it is to use the correct units, right? We said that, for example, if I asked how tall the Empire State Building was and somebody said it was 1,572, doesn't mean much, right? Is that many inches, that many feet, that many meters? So without the unit, a number by itself is pretty much meaningless. So it's really important to use units and to use them correctly. So we talked about the units for voltage, current, and resistance. Does anybody remember what the units for voltage are? Yeah. Yeah, volts, right? And that is abbreviated V. What about the unit for current?
Amperes.
Amps, yeah. The true name is amperes, but everybody calls them amps. And they're often abbreviated just with a capital A. And then the unit for resistance?
Ohm.
Ohms. And that is abbreviated omega, like you said. So these are a couple of the important concepts, the important things that we're going to be looking at throughout the rest of the semester, and these are the units for them. So any questions about what voltage, current, or resistance are, or about their units? Yeah.
What exactly is voltage again?
So voltage is the force that pushes the current through a circuit. Yeah. Yeah.
The resistance, what exactly resists for electrons to move? Or that's pretty deep.
Well,
Are we gonna follow later something? Just
so yeah, let's talk about that for a second. It has to do with the material itself and with the atoms and the electrons. So some types of materials really hold on to their electrons very tightly. So it's hard for the electrons to jump from one place to another because they're very tightly attracted to the nucleus. So with materials like that, we call those types of materials poor conductors or good insulators because it's hard for the electrons to move. It has to do with the property of the material itself. Other materials, like metals, don't hold on to their electrons very tightly. And so it's easy for the electrons to move from one atom to the next. And so those materials are called good conductors. So it really is a property of the material itself that either makes it easy or difficult for the electricity to flow.
So there's some magnetic field that actually holds them or sort of?
Well, it has to do with, it's not a magnetic field, it's actually an electrical field. So the electron has a negative electrical charge and the nucleus has a positive electrical charge. And so they attract each other. It's almost like the way that two magnets attract each other, but the electrical force is a different force than the magnetic force. So they behave kind of similarly, but they are actually different forces. Yeah. Yeah.
I have written down that amperage/current is how much electricity is flowing.
Yes.
So when talking about current or amperage, it's talking about it's the name for the measurement of how much electricity is flowing. It's not actually the name for the electricity that's flowing through, right?
Well, I guess I don't really understand the distinction.
I mean, one of it is like when talking about current, I imagine the current being like physical, like electricity moving through, and that it in itself, like the actual electricity is a current, or is it a measurement of how much electricity is coming through? Does that make sense? I don't know.
Does it depend on the battery, how much the battery is giving out?
So yes, the amount of current would depend on how much voltage is coming from the battery, but I guess I still don't quite understand what you're asking. I mean, the electricity is really the movement of electrons. So if you got right down to it, you could just call it electricity, or you could call it electrons moving along. But yeah, we call that current. When the electricity is flowing, we say that there is a current, or that there is amperage moving through a conductor.
Like water.
So,
like the example you said, water.
yeah. We
water
often
is electricity.
right.
Pressure of the water is amperage.
So yeah, I would say that
Or amount of water.
they're pretty much the same thing. Yeah. Okay. So yeah, great questions. Other questions? Okay. So we'll be talking a lot more about these later in the semester. We'll be talking about how you can use voltage and resistance to calculate current, and what the relationship is between all of these different quantities. But for right now, that's just a quick overview of kind of what they are. So let's talk a little bit about programming and some of the commands that we used last time. So last time we wrote programs to actually create Morse code. Okay? We said that Morse code was the special kind of messaging system that allowed us to send text messages over wires, or with lights, or with sounds. Last time we did it using lights. We made LEDs blink. So let's talk about some of the programming techniques that we used in order to make those lights blink. So, first of all, we used the high and low commands, right? We'd already seen those. Those turned the lights on and off, right? So we already knew about that. We also used the for next loop. What did the for next loop do? Yeah. Yeah, exactly. It caused a certain piece of code to repeat a fixed number of times that you wrote up at the top. Exactly. So you could make something happen 3 times or 5 times, stuff like that. We use the pause command to create either short or long pulses of light, and then also the delays in between. And we used comments because they were very helpful to let us keep track of where we were in the program, right? So, any questions about the programming commands that we used last time? Okay, so that was pretty straightforward then. All right, so let's move on to today's lecture, and let's talk a little bit about motors, okay? We're not going to be talking about gas motors like you might find in gas cars or things like that. We're going to be talking about electrical motors because this is a class in electronics. So, electrical motors all depend on magnetism, okay? So, with electrical motors, there is always an electromagnet, and there is often a permanent magnet as well. So, who knows what an electromagnet is? Okay, an electromagnet is a magnet that you can turn on and off. What happens is that if you take a coil of wire and you wrap it around a piece of metal, like a big nail or something like that, and then you pass a current through this wire, that makes this nail into a magnet, okay? So you were asking about magnetism before, and I was talking about electrical forces. Well, it turns out that the two are very closely related. When you have an electrical current flowing, it creates a magnetic field, okay? And we'll see later that magnetic fields can create electrical currents as well. So we'll talk about that later in the course. But right now, what you need to know is that if you have a nail like this and you have a coil of wire around it, then that electricity going through that coil will turn this nail into a magnet. Now you guys know that magnets have a north pole and a south pole, right? And that opposites repel each other, opposites attract and similar poles repel each other, right? So when you have the electricity flowing through this magnet, it creates two poles. So let's say that when the electricity flows in this direction, it creates a north pole up here and a south pole down there. Turns out that if you reverse the direction of the electricity so that now it's flowing like this, it also reverses the poles of the magnet. So now you would have a south pole up there and a north pole down there. Okay? So you can use electricity to create a magnet that you can turn on and off, and you can also determine which way the poles are facing in that magnet. So that's pretty cool. That's called electromagnetism. So this is the basis for all electrical motors. Now there are many different configurations for electrical motors, but they all work on this same basic principle. Okay? So let me show you one of the simplest configurations for electrical motors. And then we can kind of understand how this is working. So the simplest configuration for an electrical motor would be to have a shaft that's coming out of the board like this, and then have an electromagnet that is sitting on this shaft. Okay, so it's got a coil of wire wrapped around a bar of metal, and the bar of metal is connected to this shaft. Around the shaft, you have two permanent magnets. This permanent magnet on the top has a north and a south pole, and so does the one on the bottom. Okay? So what happens is that we use this electromagnet in the middle of our motor to make the shaft rotate. The way that we do that is that we push electricity through here such that we end up with a south pole up here and a north pole down there. And when we do that, these south poles repel each other, right? And the north poles also repel each other. So this forces the motor to want to turn like this, okay? So if we were to look at this motor an instant later, what we would see is that we'd still have the shaft in the middle, we'd still have the permanent magnets in the same place. But now the shaft has turned a little bit because the magnets are pushing away from each other and forcing it to turn. So now the shaft might look, or the electromagnet might look something like this. You got the south pole up there, the north pole here, and the whole thing is turning like this. Now, the south poles are still repelling each other, so it's still forcing the electromagnet to turn this way, and now the south pole is starting to get closer to this north pole down here. So pretty soon, it's going to be in this situation, where you've got a north pole and a south pole and the permanent magnet up there, you've got the permanent magnet down here, and now the electromagnet has rotated around until it's pretty much like this. And when it's here, the south pole is being attracted to the north pole, and this north pole is being attracted to that south pole. So it's still being pulled around in the same direction. But we're getting close to sort of a tricky spot, right? Because when the electromagnet gets perfectly up and down like this, then the south pole is going to be right next to the north pole. It's not going to want to go anywhere, right? And the north pole is going to be right next to the south pole. It's not going to want to go anywhere. So it seems like the motor would want to stop, but we want the motor to keep turning, right? That's what we want motors to do. We just want them to keep going around and around in a circle. So what do you think we do when the motor gets to this position and it seems to be stuck where it wouldn't go any farther?
Current?
That's right. We reverse the flow of the current. And so remember what happens when we reverse the flow of the current, we reverse the polarity of the magnet. So we have the permanent magnets on the top and the bottom, and the electromagnet is here in the middle, but since it's an electromagnet, like you said, we can reverse the flow of the current, so we reverse the polarity of the magnet there, and we end up with a south pole on the top of the electromagnet and north pole on the bottom. So now again it's repelling itself from the permanent magnets, and we're pretty much back to where we started over here. Okay? And so that's how this cycle can just keep going on, and the motor can just keep turning and turning and turning like that. Every time it gets to the point where it would almost be stuck, we reverse the polarity of the electromagnet and it keeps on moving. Okay?
Does
Yeah.
the current itself change the poles, or is that like another process?
Yeah, it is the current itself which creates the poles, and so when you change the direction of the current, that actually changes the polarity. Mhm.
Is that AC or DC or both?
Well, so we call this type of motor is called a DC motor. So we apply a DC current to the outside of the motor generally, but as you can see, the direction of the current changes quite often every time that the magnet turns past a certain point. So inside the motor, inside going around the magnet, the current is changing directions, but we call it a DC motor. Yeah. So this is, like I said, there are many different types of motors. This is kind of the simplest one. If you looked at a real motor, you would see many more permanent magnets around the outside. I only use 2 because it's easier to see what's going on that way. But in reality, you would have lots more permanent magnets around here, and so the current would switch more frequently around the electromagnet. There are also other kinds of motors where the permanent magnet is in the middle and the electromagnets are around the outside. So there are lots of different configurations for motors. There are other configurations as well that we call AC motors, but this is sort of the simplest idea, and this is the type of motor that we have inside of the servo motors that we're going to be using today. Okay? So any questions about motors in general, or this simple type of DC motor? Okay. So let's talk briefly about a specific kind of motor, which is called a servo motor. A servo motor is a motor with a brain. Okay, so let me explain what I mean. A servo motor has the mechanical parts like we just talked about here. It's got the permanent magnets, it's got the electromagnet in there, but it's also got a little computer that controls the electricity that flows through this electromagnet. Okay? So, it includes a tiny computer. So if we were to try to control the speed of a DC motor like this one, that was not a servo motor, what we would have to do is we would have to either increase or decrease the voltage that we were applying to this electromagnet. If we applied more voltage to the electromagnet, that would push more current through it, which would create stronger magnetic fields, which would then increase the attraction and repulsion between the electromagnet and the permanent magnet, which would then either cause more torque or more speed to come out of the motor. Okay? So more voltage means that the motor turns harder. Less voltage means that there's less force on that. What happens with the servo motor is that we don't actually change the voltage that we are supplying. We supply a constant voltage. And then we send little messages to the computer that is inside of the servo motor. And then that little computer handles the voltage control for us. So we might send a little message that says, okay, I want my motor to turn at half of its total speed. And the computer says, okay, I will supply the voltage that it needs in order to do that. So that's what a servo motor is. These are the little servo motors that we're going to be using. They're these little black rectangular looking motors, and they have little shafts where you can attach wheels or other parts. Okay? So that's what servo motors are. Why do we care about servo motors? Right? Why would we spend the time working on these? Well, it turns out that servo motors are used in many different applications. So if you are working with industrial robots, you're going to be working with servo motors. Servo motors are the types of motors that make robot arms move back and forth. If you are working in, if you drive an electric car, it's got a very high-powered servo motor on there. That's the way that the motor, that's the motor that actually drives the wheels, okay? It's got something called feedback, which tells the car how fast the motor is actually turning, and you can compare your actual speed to what your desired speed should be. So servo motors are really found all over the place. They can be very large, they can be very small, but they're found in many different applications. So that's why we are going to be spending a little bit of time with them. Also, they're pretty easy to use because, like I said, you don't have to handle the voltage control. You just send little messages, and then the computer interprets them and does all the voltage control for you. Okay? So they're easy to use, they're versatile, and they are found in many applications. So that's why we're going to talk a little bit about them. So one of the important things to know is how we can actually send those messages. What do we have to do to tell the motor to turn at half speed or full speed? What do those messages actually look like? Okay? So the way that messages are sent is called a protocol. There are many different types of protocols. You guys ever hear of Wi-Fi? It's the type of internet connection that is wireless. You have it in most people have it in their houses. Wi-Fi uses the 802.11b protocol or the 802.11g protocol. Okay, so those are a couple of examples of protocols. Really, anytime you want two different electronic devices to talk to each other, they need to agree on the set of commands that they're going to use to talk back and forth, and that set of commands is called a protocol. So there's a protocol for talking with servo motors as well. So let's describe what that is. The way that it works is that we send a series of voltage pulses to the motor. And then the width of the voltage pulse, in other words, the duration, the length of time that it lasts, tells the motor how quickly to turn. So each one of these pulses can be between 1 millisecond and 2 milliseconds long. One millisecond means full speed clockwise. 2 milliseconds means full speed counterclockwise. So what do you think 1.5 milliseconds means? Almost. Yeah, I heard it, but stop. Exactly. So 1 millisecond is full speed this way, 2 milliseconds is full speed the other way, halfway in between is completely still. Okay? And then there are 20 milliseconds in between each pulse. So every 20 milliseconds we send out one of these pulses. If it's 1 millisecond long, the little computer brain reads that and says, aha, I should be going as fast as I can in the clockwise direction. If it's 2 milliseconds long, it says, aha, I should be going as fast as I can in the counterclockwise direction. If it's 1.5, it should be stopped. And there are shades of gray, right? So you can be anywhere between stop and, or 1.5 milliseconds and 2 milliseconds is going to be going counterclockwise. So the closer you are to 2 milliseconds, the faster you're going to go. The closer you are to 1.5 milliseconds, the slower you're going to go, until you get exactly to 1.5, and then you're going to be stopped. You start going in the opposite direction, you start getting closer and closer to 1 millisecond, you're going to be going faster and faster in the opposite direction, and so on. So you can have these shades of gray, and by setting the pulse width, you can tell the motor exactly how fast you want it to turn. Okay? Yeah?
Is that a 1.5 or a 0.5 for stop?
A 1.5 milliseconds is stop. Yeah.
20 milliseconds, that's every 20 milliseconds have to accept a command. It's either 1 millisecond or 2 milliseconds. Or
So yeah, every 20 milliseconds you accept a command. And it doesn't have to be only one of these values. It can be somewhere in between. You know. But yes, every 20 milliseconds we send another pulse. Mm-hmm. Yeah.
So, like 1.75 would be like half speed.
Exactly.
Counterclockwise. And
Yeah.
I guess 1.25 would be the same thing.
Perfect. And don't quote me on this clockwise and counterclockwise. I always forget which one is which. But one goes one way, the other one goes the other way. Okay. Yeah.
So that would control both motors?
No, this is just one motor controlling 2 directions. It can either turn in one direction or turn in another direction. So each motor has a little cord that accepts these commands. So if you had 2 motors that you wanted to control, you would have to send out this type of command on 2 different pins. Yeah, so we'll see that in a little while. Yes?
What happens if it receives a pulse width that's outside of that range?
So I think if it's a little bit outside of the range, then so say it was like 2.5 milliseconds, I think it would still be okay. If it starts getting too big, I don't know exactly what happens. I think it would just not understand it and it might stop turning, but I'm not 100% sure. Yeah. Other questions? That's a great question. You could try it out and see. That's one of those places where you could definitely experiment and find out what happens. Yeah. Okay, so this is the type of signal that we have to send to our servo motor to get it to move. So let's see how we can use our programming language to actually send those kinds of signals. So the command that we use to create very short pulses like this is called pulse out. Okay? you'll notice that there's no E in there. It seems like there should be an E, but there's no E. So pulse out. So the syntax of the command is pulse out and then pin number and then pulse width. And the thing about the pulse width, seems like we're talking about milliseconds, it should be in milliseconds, right? But they don't make it that easy on you. It's actually given in clock cycles. So we have to do a little bit of conversion, and we'll talk about that, okay? So a 750 clock cycles equals 1.5 milliseconds. Okay. Another way to say that is so that's the way that it works. So if you said pulse out 14 and then 750, that would send out a 1.5 millisecond pulse on pin 14. Okay?
The clock cycles of the microchip?
Yeah, of the microchip. Yeah. So that's how it works. So let's see some real world examples here. Okay? Like I said, the goal of today's lab is to make the motors go back and forth almost like windshield wipers. You only have to do it with one motor. So your goal is to make one motor go back and forth like a windshield wiper on a car. Let's see how we can do that. Again, we're going to give you some code to start from. We're not going to make you start from scratch. So the code that we're going to start with today is here under ET302, L02 stamps, and then windshield wiper. So let's just run this code first of all and see what it does, and then we can talk about how it works.
You said ET302 what again?
L02 stamp 2 and then windshield wiper. Okay. So we're going to do the three things that we have to do before we program our robot. We're going to plug in the battery, which I've got up here. We're going to plug in the serial cable, and we're going to turn it on. Now, in the past, we've turned the robot on using either position 1 or 2. It didn't really matter before. But today, it starts to matter. Okay? So the reason is that position 1 turns on everything except the motors. Position 2 turns on everything including the motors. You might say, why is this important? Well, what happens is that right after you send the program over, the program starts to run. So if you've got your board on in position 2, and you send over a program that tells the motors to run, and you've got the motor lying on the table, then as soon as that program comes over, the motor is going to turn on, and it might roll itself right off the table. Okay? So it's a good idea to program the motor, or program the stamp with the switch in position 1, because that allows you to send the program over and it keeps the motors off, and then when you're ready, you can move the switch over to position 2 and turn those motors on. Okay? So that's what we're going to do. We got it turned on in position 1. We've got the windshield wiper program opened up here, and I'm going to run this. So I'm going to send it over, and then I'm going to move this over to position 2, and it looks like I've got my servo motors plugged into the wrong place. Okay, so without going into too much detail on the code, we can see that we're looking at pulse out on 12. So that means that we're sending commands over on pin 12. Up on the top of the board is where you can attach your servo motors. There are these little sockets that have positions for servo motors. And, well, okay, so it looks like I do have a motor plugged into pin 12. So you can see that the pin numbers are listed along the top. So the one on the far left is 15, then 14, and then 13 and 12. So looks like I do have my motors plugged into the correct places. So what's going on here? Okay, I guess I just let it run too long and it finished before I was able to see it. Okay, so we'll do this one more time. If you want the program to start over, you can hit the little reset button on the top of your basic stamp. So it went one direction, and then it went the other direction. So we were able to get the motor to move. Okay? So that's a pretty good step in the right direction. So let's see what's actually happening with this code. See how it works. So we'll go and make the font a little bit bigger here. Not quite that big. All right. You guys see that okay? All right. Cool. So we start off with an initialization. Initialization is the name for something that we just do once at the beginning of a program. So we say low 12. This says it sets pin 12 to low output. So then we're looking at this if statement. We'll talk about if statements in a minute. But after that, we go on here and we are actually using a for loop. So you guys remember that we used for loops a little bit last time. We said that these were commands that allowed us to repeat something a certain number of times. So inside here, we're using the pulse out command. So we do pulse out on pin 12 and 500. So this is sending a message out on pin 12 where we have a motor connected, and it's sending out a value of 500. So 500 would correspond to 1 millisecond, so that would be full speed in one direction. Okay, so this pulse out command is telling the motor to move at full speed in one direction. We'll call it clockwise. Okay, so we're going full speed clockwise here. And then we have this pause 20. What do you guys think this pause 20 is all about?
To pause until you set it for the second motion?
Not quite. Not quite. It has to do with the protocol that we talked about earlier. So, you guys remember using 20 in the protocol anywhere?
Yeah, 20 milliseconds.
Yeah, right, 20 milliseconds. So this pulse out creates this pulse, and then we have the pause 20 up here, which is the delay from one pulse to the next. Okay? And then we repeat this. So then we create another pulse and have another pause and another pulse and another pause and so on. So that's how we are creating one pulse after another after another. Okay? And how many pulses do we create altogether? 100, exactly. We do this, it's in a for loop that runs 100 times. Each time it runs, it creates one pulse, so we create 100 pulses altogether. So why would we create more than one pulse?
One pulse is very short.
That's exactly right. One pulse is very short. The motor stops moving once it stops receiving pulses. So if we only sent one pulse, it would move for just a split second, and then it would be done. So in order to get it to move for any length of time, we have to send it many pulses. So what would we have to do if we wanted it to move for longer?
200.
One pulse?
Yeah, you could increase the number of pulses to 200 or 300 or whatever you wanted. So more pulses means the motor is going to be running for a longer time. Less pulses means the motor is running for a shorter time. Okay? So this number of pulses that we have up there determines how long the motor is going to run. So let's play around with that. Let's make this, so we'll run this one more time just to see, remember how it goes. So it runs forward, and then it runs reverse, and then it stops. If we change this to 50, say, 50, now we run it again, goes forward, stop, reverse, stop. So we can affect the amount of time that the motor is running. What would we do if we wanted to change the speed that the motor was going? That's right. We would have to change something about this pulse out command. What would we change about it?
500.
Yeah, the 500, right? We said that 500 corresponds to 1 millisecond full stop. Or I'm sorry. 1 millisecond, which was full speed clockwise. So we could think of this as kind of a scale, right? So down here on one side we have 500, which is full speed clockwise. On the other, right in the middle, what do we have right in the middle? How many clock cycles down here? 750, exactly. This is stopped. And then over at the other side, how many clock cycles would we have for full speed the other way? 1,000. So we'll call this full speed counterclockwise. Okay, so you can play around with the speed that the motor is running at by changing these numbers there. Okay? All right, so So that's a little bit about how the motor is actually being controlled. So let's see. So what we're going to do is we want to talk briefly about if statements. If statements allow us to send some information into the microprocessor. So what we want is we want to have like a switch on our windshield wipers. We don't want our windshield wipers to run all the time when it's dry out because they'd scratch up the window, right? We only want them to turn on when it's wet. So we want to have a switch that allows us to either turn those windshield wipers on or turn them off, okay? So what we're going to do is we're going to use a little wire here that we call a jumper wire. And we are going to use this to send either a high voltage or a low voltage to one of the pins. Okay? So this if statement up here is talking about in 1. So this is looking at pin number 1. Okay? So we are going to attach a jumper wire to pin number 1. And this jumper wire is going to be our switch. So it doesn't look like a switch that you've seen before, but this is going to be the switch that we're going to use today. Right? So we've attached one side to pin 1, and now we're going to attach the other side either to a high voltage or a low voltage. And then the microchip is going to be able to read that and tell whether it's a high voltage or a low voltage, and it'll make a decision based on it. So this says if in 1 equals 0. What that's saying is that if in 1 is low voltage, then do this. So if in 1 is low voltage, then we run the windshield wiper clockwise and then counterclockwise. Right? And then else is down here. It says low 12 and low 2. So else, if we have a high voltage, we're going to turn it off. So basically, this little green wire is going to be a switch. If it's connected to a low voltage, the wiper is going to run. If it's connected to a high voltage, the wiper is not going to run. So let's see how that works. So I'm going to connect it to a low voltage first. I'm going to connect this over to VSS. Now I'm going to hit the reset button and we should see the motor run. So, yeah. So the motor is running. Okay? So when the switch is connected to a low voltage, the motor runs. Now if I connect it over here to VDD, that's a high voltage. So when I push the button, the motor should not run. So sure enough, I'm pushing the button and nothing's happening. Okay? So that's how we can tell the motor whether to run or not. Okay. So you guys are going to have a couple of challenges in this lab. First of all, you want to make the motor actually work like a windshield wiper. So a windshield wiper goes back and forth, from one side of your window to the other. It goes back and forth about like this. If we run the program right now, we're going to see that the motor goes a lot farther than that. So when we run the program, the motor goes almost an entire rotation right now. So you are going to have to change the program around and fix it so that the motor only goes 180 degrees back and forth. Okay? So you guys will have to play around with that. Remember, oftentimes if you're working out in industry, you get a piece of code to start with, but that code has some bugs in it. So that's kind of what you get here. You got some code going. It shows you how to make motors move, but it's not working quite right. You guys are going to have to modify it and fix it so that it does what you want it to do. So you're going to have to make it work so that it goes from one side horizontal to the other side horizontal and back. And you'll want it to do that over and over again. So you'll want that to happen at high speed. And then, once you do that, you will want to modify your code and also make it go back and forth at low speed. This is kind of like, you know, either the windshield wipers going back and forth when it's pouring down outside, or back and forth very slowly when it's just kind of drizzling. Okay? So you will want to make the code work so that it can go back and forth very fast or very slow, and you want to be able to use your switch to choose between those two settings. So, so if the switch is in one position, it will go back and forth really fast, and if it's in the other position, it'll go back and forth very slowly. Okay? So that's going to be the big challenge for today's lab. So do you guys have any questions about that? Yeah.
I have a question about the signal we see.
Yes.
So there's like something wrong with the signal. It's wrong pole. So how we will know that we are sending the wrong signal? Like it's not, maybe we are sending not 20 milliseconds, we are sending 19, but we can. Is it all will be like visual in this, or there is some way that we can see it? Tell us that we are doing right.
There is a device that you can use. It's called an oscilloscope. We have not worked with oscilloscopes yet this semester, but we will start working with them later on in the semester. If you're interested, once you get done with the lab, you can call me over or one of the other lab assistants, and we can show you how to actually see the signal on an oscilloscope. So we'd be happy to do that. And you'll be learning more about them later on, and by the end of the semester, you will know how to do that all by yourself. Yeah? Yeah?
What was the green wire for?
The green wire was the switch. So this initial program that we looked at was using the switch to either turn the motors on or off. So this switch was, one side was connected to pin 1, and then the other side was either connected to VDD or VSS, high voltage or low voltage. So the wire is either connecting a high voltage or a low voltage to pin 1. Okay? Our program is looking at pin 1, and it's looking to see if there's a high voltage or a low voltage at pin 1. So this if statement is what is looking at that voltage. The statement says if in1 equals 0, then do all of this stuff. So in1 equals 0 means that you have a low voltage there. So it's saying if you have a low voltage, then do all of this stuff. Make the windshield wipers run. And then down here we have this else statement. This is actually part of the if statement. This says if the first thing is not true, then do this other part. So if the voltage is not low, then do this thing down here. Basically turn the servo off and turn an LED off. So you guys can hook up an LED also to show you whether your motors are supposed to be on. Okay? So if the voltage is low, then run the wipers. Else, if the voltage is high, turn everything off. And then finally, this end if statement shows that you've reached the end of the if condition. So So that means that everything is over and the next part of your program could begin. If there was another part of your program. Okay. Any questions about that?
Pretty much we can run it without that green wire, the switch, but the switch is kind of represented as the wipers, as you mentioned.
Right.
It's kind of confusing, you know, that the wire for on the beginning, but
Yeah.
so we can run without that wire, but with the wire it's kind of like
Well-
switching the car, sort of to turn it on or off whenever you need. Not gonna because it's gonna run all the time or nonstop, something like that.
Right, so if you don't have the wire attached, then you have a condition, basically an unknown condition. So that voltage at pin 1 might be high or it might be low.
Also, it actually tells them that you get on.
Right, and so your program might behave in unexpected ways. It might do the high thing one time, and then the next time it might do the low part, because there's nothing connected to that pin 1. So the voltage on pin 1 can do what we call floating. It can kind of, the voltage can go up or can go down depending on, you know, the static electricity in the air, or whether somebody bumped against it, or things like that. So it is important to have the wire there. I got lucky when I was running it earlier in the class, and it happened to be in the state where the motor was running, but it is not necessarily going to be that way. So it is important to put the switch in. Okay? Does that make sense?
So even with that command, we can program to run faster or higher voltage, lower, like, you know, like wipers has different stages. They can go faster or slower.
Right, right.
So even then, we can get program even more complicated and just switch the wire and you can go faster or slower.
Yes.
Whichever we need to choose.
Yes, exactly. Yeah. In the book, they show a more complicated diagram about how you would connect a switch. So in the book, the diagram looks like this up here. Okay, so they are using a resistor and then another wire over here. And there are reasons that they do that, but this is just a more complicated way of setting things up. And it's not really necessary. So I would recommend not doing it like this. I would recommend doing it the way that I showed you in class. Yeah.
Question about VDD and VSS. So that the VDD is high voltage and the VSS is low voltage.
Yes.
I've been understanding it as like positive, negative, VDD being positive, VSS being negative. Is that correct?
VSS is really ground or 0 volts. Okay. But yeah, VDD is a positive 5 volts. Yeah.
So, I noticed that the motor was pin 12.
Yeah.
But there's also the pins on the breadboard go up to 15.
Yeah.
So how do you distinguish between that pin 12 and the other pin 12?
There is no difference. They're actually electrically connected to each other. So if you were to measure the voltage on the pin 12 that's up here at the top of the board, and then measure the voltage over here on the pin 12 over there, you would see the same thing. You would see pulses coming out of this pin 12 when you're sending them up here too. The reason that we have these sockets up here is because they are specifically designed for servo motors to be plugged in. That brings me to something else I wanted to show you about servo motors also. Servo motors have cables that include these 3 wires. There's a black one, a red one, and a white one. The black one is ground, the red one is power, and then the white one is the signal. That's where we send the pulses. So we have these little sockets to make it easy to connect these 3-wire servos to our board. the thing I wanted to point out is that it's actually possible to plug the servo motors in two different ways. There's nothing to prevent you from doing it two different ways, but it's only going to work if you plug it in the right way. So the way that you can tell which way is right is you have to look at this little tiny writing that is next to the sockets. So on the bottom it says black, in the middle it says red, so you have to line up your cable so that the black wire is on the bottom and the red wire is in the middle. So you have to plug it in like that. And if you plug it in backwards, it's not going to damage anything, it's just not going to work. Okay. Yeah?
Do you explain what ground is?
That's a good question. So ground is a name that we give to a certain part of our circuit. And then when we're measuring voltage, we measure it relative to that point. So oftentimes we call ground, we say that ground is the lower voltage on our battery. Okay? So if we have a battery, it's got two terminals, and one terminal has a higher voltage than the other. So oftentimes we say that ground is connected to the terminal with the lower voltage. That's what happens in cars. The lower voltage from the battery is connected to the chassis of the car. That's why when you're jumping a car, you can connect the positive jumper wire to the positive terminal of the battery, and you can connect the other jumper wire to the chassis of the car. Because the chassis of the car is electrically connected to the other terminal of the battery. The battery terminals are often called positive and negative, but like I said, we often attach the name ground to the negative terminal, and then we call that point 0 volts. And we make all voltage measurements relative to that point. So if we measured the other terminal of the battery, we would say that was a 12 volt voltage at that point. But really, ground can be any point in our circuit that we want. With older cars, the standard was to call the positive terminal of the battery ground. And so with some older cars, the positive terminal was connected to the chassis of the car, and then the negative terminal was separate. So this was from before 2000, way before 2000. Certain cars were hooked up this way. So really, ground is just some arbitrary point that we define on our circuit, and then we make voltage measurements relative to that point. Sometimes we have a circuit with two batteries in it, and ground might be the point right in between those two batteries. So really, ground is just, sometimes it has no physical meaning at all. Sometimes it's just a point that we pick on the circuit. Sometimes it does have a physical meaning where that part of the circuit could be attached to a chassis. Sometimes, like with wall outlets, when we talk about ground, we're actually referring to a piece of metal which is a physical spike driven into the earth. So that's where the name ground comes from, because it's attached to a piece of metal in the ground. But oftentimes when we're talking about small circuits, when we refer to ground, it has no physical meaning. It's just one particular point on the circuit.
So if you had two circuits and let's say the ground voltage on one is higher than the other, and you apply 12 volts, like you use a 12 volt battery, it still measures 12 volts on both relative to the ground. Like ground isn't like a universal like 0, it just is only relative to that device, right?
Right, ground is not a universal thing. So you could have one circuit with its own ground and a separate circuit with a separate ground. And if you took a voltmeter and measured between those two, you could see a difference in voltage. So ground is not a universal thing. If you have two circuits and they're going to work together, you almost always want to tie those two grounds together so that they are at the same potential. Otherwise, it can start doing weird things. There are problems called ground loops when the ground is not the same. So it is not a universal thing. Yeah.
Another question about what determines whether or not the positive or negative is higher voltage than the other. Does that have to do with conventional or electron flow? Or what actually
No,
determines which one is
we
higher?
always say that positive voltage is higher than negative voltage. Conventional flow just says that electricity flows from the positive voltage to the lower voltage, and electron flow says that electricity flows from lower voltage to higher voltage. But positive is always higher. Yeah. Other questions? Okay. Cool. Then I will take 10 minutes and then I'll let you go.